I gotta slow down. Brad, is this a standard inner product? What number is this? 17? You know what? He didn't say. And if this author doesn't say that it's going to be unusual inner product, he just means it's understood as a standard inner product.
Okay.
So that's what he meant, even though he didn't actually say it. So using a standard inner product, let me look at the inner product of these two. I guess it would be 1 plus 0 plus 1 plus 0. But if I were to look at the inner product squared of u1 bar with itself, wouldn't that be 1 plus 1 is 2? Okay, you guys, so the arithmetic's really easy in this example. I apologize. That being the case, I think I'm merely left with 1 comma 1 comma negative 1 0 minus my 1 0 negative 1 0. Or shall I just simply say, is that going to be a 0 comma 1 comma is that a 0 again? You guys, I just performed a lot of arithmetic. I might have made a mistake. Can I just double check real quick? See if I made a mistake. Let me just check orthogonality with these two. Oh shoot, I just computed the inner product. I got 0. So far so good. Michael?
What, the thing in the brackets, the thing you're subtracting at the second line, could you write out what it actually is doing? Like you said it was the projection of something to something else.
I was just simply suggesting that with this big circle in green, I sometimes merely refer to this as the projection of my V2 bar onto my U1 bar. And by the way, that's exactly how you refer to vector projection back in trigonometry. We just didn't use the funky notation right here. We just used what we refer to as a dot product. It's just the inner product's a generalization of the dot product. That's why I'm using the same phrase, projection of V2 bar onto U1 bar. Oh, I forgot my one. Hold it. Chris?
Would you be okay with us using column vectors to represent our vectors instead of the row vectors, just to save space?
It's 100% irrelevant. It really is, because you're still in the same dimensional space. So you use whatever notation is more convenient for you. Well, of those two. Just be consistent throughout. Oh, you guys, I haven't done the big work.
No.
Actually, for me to find U3 bar, I'm just going to proclaim that U3 bar is V3 bar. Minus, listen to the way I say this in English. Minus the projection of V3 bar onto U1 bar. But also minus the projection of V3 bar, onto U2 bar. And I apologize, you guys, I've got a bit of arithmetic to perform. So the arithmetic, I'm going to come in and restate what the heck V3 bar is. Not that I can possibly remember. Remember, no glasses. Is it negative 1, 1, 0, 1?
Yep.
Yes. So it just continues on like this. So say you had like, there's V5 or whatever. You just do the same thing except with multiple terms as you kind of progressively go down the numbers. So it just gets longer and longer and longer.
Do you think, instead of just saying it in words, can we write a mathematical? I know.
Is there a way of doing it with sigma? I guess, or series.
Yeah.
Did you? You did that?
Here's what I wrote. I wrote
Okay.
that VN bar.
Okay.
I'm sorry, I misspoke. I meant UN bar is nothing more than VN bar
Okay.
minus the projection of VN bar with U sub I don't know, I bar.
Okay.
As I range from 1 to
N minus 1.
yeah, not quite n because I'm just subtracting off its predecessors. This way I can generalize this if I really had n vectors.
Okay. That's cool.
Oh, but you guys, I really messed up. I got a lot of arithmetic to do. I guess I got minus a fraction times U1 bar, which is 1, 0, negative 1, 0. Can I stop and do the arithmetic? The inner product of V3 bar with V1 bar is going to give me a negative 1 plus 0 plus 0 plus 1. Isn't that a big 0?
0 at the end, so it's
Sorry, it is 0 at the end. Thank you. So I really just lined up with a negative 1. And the magnitude of U1 bar, I already computed in the last example, it was a 2. Oh, I got to keep going. Hold on. Let me give myself some room. I now need to subtract off a fraction times U2 bar, and U2 bar I just found to be 0.100. But the fraction up front is the inner product between V3 bar and U2 bar. That inner product is simply going to be a positive 1. And I think the square of the magnitude of U2 bar is simply going to be, actually positive 1. And so I guess I've got a negative 1, 1, 0, 1, plus a negative 1/2, 0, positive 1/2. Uh-oh. Nope, I've got a sign error. I didn't see the two negatives. Minus, or shall I say plus, my 0, negative 1, 0, 0. Which I think in the end gives me this 4-element vector whose components are negative 1/2.
Wait, why would you change it to plus and then?
It was just convenient for my arithmetic. I'm really tired, so I changed it besides the inside so I don't mess up my arithmetic. I think my second entry is going to be a 0. The third entry is going to be a 0 as well. And lastly, the last entry is going to be a positive 1. But there was arithmetic involved. Yet again, let me take a break. Let me look at the inner product between my U1 bar and U3 bar. It better be 0. Okay?
I think the third element should be negative 1/2.
Did I mess up? The third element should be negative 1/2.
Yeah. Yes.
It clearly is. My apologies. I still messed up my arithmetic. There might be another error, so just double check. First and third, it checks out. This in the third, it checks out. I've got orthogonality. What if I asked you to give me an orthonormal set of vectors spanning the same subspace of R4 as V1, V2, and V3?
You just multiply them by their magnitude.
Yeah, you just multiply each of these by their
by the reciprocal of their magnitude. Yeah.
Divide by their magnitude.
Yeah.
I agree.
So you don't mind if we like the book always writes it with the magnitude like factored out. So it's just like the reciprocal of the magnitude and multiplied by the vector. Is that fine, or do you like it all in just like
You know, really, I
1 form?
100% irrelevant.
it's 100%?
I really wouldn't care whatsoever. When
Okay.
I'm grading exams, I don't insist that you have it 1 form.
Okay.
You guys gave me a hard time with this yesterday. So can I throw it at you again?
I have
Yes.
one more homework problem, more question.
Look at this first. I'll come right there. If this really is an orthonormal set, it's a basis for some subspace. What can you say about this?
Well, it'd be 0.
Will it?
If they're orthonormal.
So long as I'm there.
What if they're the same vector?
What's that?
What if they're the same vectors?
If I equals J, then it is 0.
Then it's equal to 1. Okay, so give me your answer.
It's always equal to 1.
If I equals J.
Ooh, too many words.
Oh, one if I
Delta
equals
I
J.
sub J
Yeah.
will-
Okay.
Chris, I'm being silly.
I know.
But you see my point. Okay.
So that's just 1 if I equals J and 0 if anything else.
Yes, using my product of delta notation, I'm simply implying the value is either 1 or 0, depending on whether or not I is equal to J or otherwise.
Can we write either of those, or just the product of delta?
Don't you be sophisticated?
No.
Yes, you do.
Okay.
I know you do.
Number 21.
Same section.
Yeah.
Number 21. Oh, you guys, please don't write what I'm writing yet. I'm sorry. I'm being so sloppy today. So determine orthonormal basis for the subspace of C3 spanned by the given set of vectors. Make sure that you use the appropriate inner product in C3. But you guys, tell me what C3 looks like. What does the space look like right here? Hold it.
What kind of C? Complex C? Alright.
Before you even answer the question, let's talk about what it looks like.
Set of complex numbers in degree 3.
What do you mean by that? I'll be honest. Because you said of degree 3. I don't know what the degree really
It's
means.
not degree, it's where the
It's
dimension
where-
is 3.
Thank you, your dimension is 3.
Yeah.
Well, I think I should not have said that. I meant to say, you've got 3 components.
Yeah.
So do you normally, when you write your complex C, do you normally just put the line through and is that why it's complex? Is that for your notation? Because I know it could be constants as well.
You know, what a good question.
Can
What
be
is your
continuous,
author
couldn't
print?
Yeah, or continuous, yeah, so.
Well, continuous is C
Because we'd use
dot.
integrals and, yeah.
Yeah, when it comes to continuous functions, I wouldn't
Yeah.
necessarily put a bar through there, because when I put the C with a bar, I'm referring to the complex numbers.
Okay, and so without a bar, it would be continuous?
Be a set of continuous functions.
Okay.
The vector space of continuous functions. Now, personally, the bar notation I think is kind of horrible. If I were a textbook, I wouldn't use this notation. I would use a boldface C. I just can't do it on the inkboard, so I put that vertical slash on the left-hand side so you understand it's a set of complex numbers. I confess, and I apologize, you guys, if I don't look at your book very carefully, being the professor. But I didn't realize he doesn't boldface. He does something very similar to what I'm doing to represent a set of complex numbers. Usually, you don't see it printed the way he's printing it. Usually, you'll see it as a boldface instead. So you understand it's complex
Okay.
numbers. But you guys mind if I don't answer the question yet? Because I think this is something I have not discussed yet in class. I don't even think I mentioned that. I've left it for you as reading. But check this out. Is this in here? Yes, I think it is. And to discuss its magnitude. To discuss its magnitude in such a way that it makes sense. Wouldn't I get this?
No,
Well, no, hear me.
you wouldn't. Because you'd be dividing by a negative number if you did that.
Oh, it's worse than
Yeah, it's, the world would end and,
Dividing by 0 plus I squared.
that. Sorry, I'm so slow.
1 minus I squared.
Do you guys see my point? I mean, when it comes to a standard inner product I have an R3, I think things are really tough. Because technically speaking, I got all I's in the integrand's position. Maybe not an I here, that's just -1, I don't care about that. And here's another -1, here's another -1. But in the end, I'm left with 2I minus 1. It's got an I in there. Now, is this thing strictly positive?
Well,
Well, what?
you miss minus 2i in there, and they would have canceled it out.
My goodness. Okay, so this time I got lucky. They end up canceling. They don't have to. They generally don't. But I'm still left with a -1. And I think what I really want is to make sure that the magnitude of a vector, no matter what my vector space is either going to be 0 or positive. And so I think if I use my standard inner product operation that I had in Rn, it's not going to work with complex numbers. So just because I want to get around this, here's what I have a tendency to do. When it comes to inner producting one element like this with another one, when it comes to the inner product, I have a tendency to say it's Z1 times Z4 plus Z2 times Z5 plus Z3 times Z6. I just made a mistake. The mistake I made before. So to get out of the trap, I make sure the second complex number is its complex conjugate. It allows me to actually think of the magnitude of a vector, that is to say, inner product with vector with itself, to come in and look at complex conjugates. And so that everything is meaningful.
I times
And now if I go through my computations, let's see what it generated. Oh, no, my life is really easy. These are the factor form of difference 2 squares. I think I've got a 1 minus I squared.
Which is
I
1
squared
plus
is
1.
-1. Plus, a 1 minus I squared. But again, I squared is -1. Minus I squared, which is the same thing as minus -1. I get a number that has meaning to me as positive. Complex numbers are kind of tricky. If I gave you two complex numbers, I misspoke, let me take that back. If I gave you two real numbers, A and B, on a number line, could you tell which one's bigger than the other if they're not equal to each other? If they're not equal to each other, can you tell me which one's bigger on a number line?
Yeah.
I think emphatically yes, because one's going to be located here, one's going to be located here, or vice versa. There's order in the number line. But when it comes to complex numbers in the Gaussian plane, I think we're in trouble. Here's the real axis. Here's the imaginary axis. Here's a complex number, z being equal to 1 plus 2i. There's this location in the Gaussian plane. Well, okay, there's this location. Jeepers. Yes, Chris?
Maybe you're going here, why don't you just compare the modulus of every...
Oh, that's where I'm going. But I'm going to show you it's going to cause problems.
Oh,
How about considering this complex number, I'll call this one z2. How about this one z1, z2, excuse me, 2 plus I. I haven't made any mistakes, you guys. Those are their locations in the Gaussian plane. But my question is this, which one's bigger? Because they're not equal to each other. Like the A and B in the number line, they're not the same complex numbers, just like A and B were not the same real numbers. But how can I possibly order these? Because I think their modulus in each case is going to be the square root of 5. And so sometimes in mathematics we refer to the complex number system as a system in which we do not have such order. As a matter of fact, in the Gaussian plane, you tell me how many complex numbers have a modulus of positive root 5. I said, you tell me how many numbers in the Gaussian plane have a modulus of positive root 5.
What's the modulus?
Modulus is just the length of a complex number. It's distance from the origin. It's distance from the pole. Chris?
You said it break apart, but can I go for what?
Of course you have.
Recipe. What if you did something like, I mean, this isn't really strictly order, but it's kind of order because given any two sets, you know if they're in the same position or you know if they're one greater than equal to. If you started dividing them all the points in the plane by their radius, and then you made your ordered set, you know, make it a set of sets where you have all of them with a particular radius one, and then you.
Okay, now I like that. The only problem is that what are you going to do with each of those small sets? Like the set containing the R1s.
You say that they're all in the same place.
Okay, I sometimes say in algebra they live in the same class.
I don't know what it means, but okay.
I'm using fancy words saying what you're saying. It's just, I think with that first set though, the problem is I can't order them. And I want to be able to order all the complex numbers.
Is it really useful for that? Be able to order things?
So you're dividing each
Yeah,
one by its
it's a
radius?
very strong, unique property within the real number system. I shouldn't say unique. It's a very strong property of the real number system that the complex number system does not have. So what I want you guys to say this, you never answered my question. To answer my question, how many complex numbers in the Gaussian plane have a modulus of root 5? Infinitely many. And that being the case, I just can't order the complex numbers straightforwardly. I can do what Chris just suggested. I can talk about the class of these complex numbers that have the same modulus, and I can order those classes, but I can't order the individual components, the individual elements, the individual complex numbers. Pretty cool stuff, I think.
So when, instead of like just using Z4, you do the complex conjugate of Z4, will that always give you numbers like that don't have I in them now when you then multiply it? Like what if the...
It's for free. What I said is going to work every time because check this out. If Z is equal to A plus BI, then its complex conjugate is going to be A minus BI, but when I multiply those together, I got the factor form that gives us 2 squares.
Yeah, I'm wondering though, like, when you say like the complex conjugate of Z4, does that mean complex conjugate of then Z1?
No. I meant look at the inner product of these two elements of C3. This Z4 is different than Z1, but I'm going to use this complex conjugate when I compute the inner product. That's all I meant.
What if its complex conjugate wouldn't give you a nice answer? Like, what if Z1 was 1 plus I and Z2 was 1 minus I? Then the complex conjugate of the second one would give you
What's the deal there? HTTPS. HTTP : // You don't need an S.
Do you want me to write what I mean then?
No, I see your question, because I have to admit, when I was answering your question, I was only looking at the inner product of an element with a self.
Yeah.
And therefore you get things canceling with the pairs. But regardless, this is still the way we're gonna define the inner product, so that when I inner product with an element with a self, I can eliminate the i's. And that's the whole point.
So you only need to multiply it by the complex conjugate when you're multiplying two complex numbers. Like if you had a real multiplied by a complex, you would just be straightforward. You wouldn't have to switch the sign.
I don't know.
Like if you had,
I can answer the question both ways. I can say, this whole notion of complex conjugate business still works when all the entries are real numbers. Because I think when it comes to real numbers without the imaginary components, it is the same as what we had last time in class. Because I think when it comes to an a plus 0i, its complex conjugate is just, it's just a. Minus 0i, which is just still an a. And that's why this new version with the complex number system still works with the real number system. It still works with Rn because it doesn't change anything from what we had before. But the upside is it allows me to consider one complex number z1 multiplied to its complex conjugate, the same number, but just conjugate. Then I get rid of the i's so that I can start talking about the magnitude of a single vector. And that's the punchline. I'm sorry, I never answered the question. So can we come back? So I am going to allow v1 bar to be this beast. I'm going to allow v2 bar to be this beast. U and I will automatically set u1 bar to be nothing more than v1 bar. You guys all be better with my color. Is my black working? But my u2 bar is going to be nothing more than my v2 bar minus the projection of v2 bar onto u1 bar, all divided by u1 bar's magnitude twice, times my u1 bar. Let's play. I think this gives me, is that a 1 plus I comma 0, minus a fraction, where the actual vector u1 bar is given as 1 minus I. 0i? Okay, guys, let's slow down. I need to come up with the numerator, or what's in the numerator's position. I'm going to take a peek and look at the inner product between v2 bar, which is right here, with the other vector u1 bar. Well, actually, u1 bar's got components that are conjugates, and so I think I'm going to look at the conjugate of this piece right here. All over the inner product of my u1 bar with itself. Now, if you guys don't mind, let's get down to business with the arithmetic. Now, performing the arithmetic, I think I'm going to multiply these two components. That's 1 times 1 minus I. What's next? What's next?
Nothing.
No, I think next is to fix my mistake. Where's my mistake?
You're not, are you actually multiplying by the conjugate there? Because that
And I have
doesn't
it.
look
That's
like
the
the
point.
conjugate, yeah.
So now when I look at the inner product of these two beasts, it's the product of the first with the complex conjugate of the second. You guys see my point?
Perfect.
Plus the product of the second component of the first vector, I'll leave it as is, times the complex conjugate of this component of the second vector. Okay, it's a little silly here. Plus the third component of the first vector, which is 0, times the complex conjugate of the third component of the second vector. I know if I made a mistake there, you wouldn't see it because it's multiplied by 0. I'm just trying to impress upon you, I've got to deal with the conjugates. All over downstairs. Oh, let's do this one fast. It's a 1 minus I times 1 minus I times, or plus 0 times 1 minus I, plus, hold it.
Wait, you're not doing conjugates
yeah,
again.
you're not doing.
I mean, this times this, plus this times this,
But
plus this.
You want to be multiplying by your
Times this.
conjugates, right?
What's that?
You want to be multiplying by your
Okay,
conjugates,
good.
right?
Here too, even though the same
And then
vectors, the second
also,
one's
you want it to be, well, because you square the magnitude, so you're just leaving out the square root, right? That's,
Yeah, is that okay?
okay, yeah, that's
Means
fine.
same thing. Oh, I forgot my vector. And I suppose in the end, that's merely going to give me, actually, I have no idea what it's going to give me. Ay, ay, ay. Help me, guys, is it 1? 1 plus I, 0. Is that right?
Yep.
Mhm.
Actually, I have no idea what this fraction is. Has anybody computed it?
1 plus I over 3.
So just 1 plus I period. Over what?
3. Right? Because 1, 1, 1.
Yeah, I agree. I'm just a little slower than you are. Multiplied by 1 comma 1 plus I comma 0. You guys, am I getting to crunch with a broom? Is this okay?
Mhm.
That gives me 1. 1 plus I. 0. Minus 1/3 times, let's play. Yes.
The last vector, isn't it v or u1?
It is U1, yeah. Okay, so you're saying when I came in and copied this triply underlined vector off the board, I have no idea where I got that, sorry. I just copied what I have. Well, let's compute. Let's compute.
1 plus 1 plus 1.
Which is 2. Thank you.
0. Negative I.
Negative 1.
What's up? What happened to 1 times negative I? What's up?
Plus I. Because 1 times I is I, but I times I is negative, or it's I squared, which is negative 1. Am I doing okay, you guys? If I am, I guess in the end what that really gives me is that going to be a positive 1/3? Oh, this was easy. Oh, come on. It's not that nice, is it?
Where did your last term come from?
Where did my what?
Last term.
Last time.
0 minus 1.
Oh, you guys, I'm multiplying them. I'm so sorry, I gotta take that all back. Cheapers. Ay, 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 I'll be quiet. What do I have left over for the second slot? Yeah, in my head, I was multiplying this to this. And what about my very last slot?
1/3.
One positive 1/3.
Minus 1/3.
I agree. I'm nervous. I just blundered a couple times. So can I just double check my work? Let's see, if I'm looking at the inner product of this blue beast with that black beast, remember, it's these individual components multiplied to these individual components after I look at their conjugates. So just to check for my orthogonality. I guess that suggests that I'm left with my 1 plus, or 1 minus I, times, say that loud.
1/3.
Plus my 0 times, who cares? But finally plus my I times, what is that, 1/3 minus 1/3 I? Good, I gotta consider the complex conjugate. Or shall I say, 1/3 I, excuse me, 1/3 minus 1/3 I, plus 1/3 I, plus 1/3 I squared. Oh, thank goodness, you guys, it divides to 0.
So,
So I've got orthogonality.
on a check or on a test, would this check just be for our own purposes, or would it be necessary to actually show orthogonality?
I would not require whatsoever.
Okay.
If you feel confident with arithmetic, go for it. I'm in front of class, I'm the professor. I check mine,
Okay.
because I make these blunders all over the place.
So on a test, because the question was find an orthogonal basis, right? Use the Gram-Schmidt notation to find an orthogonal basis. Is that,
And I did.
And so for the notation, would you just want to put the brackets around that vector?
How about braces around the vector?
Braces, I mean,
So
sorry.
I guess if you really want my final answer, I would have said, well, the corresponding basis is nothing more than set containing this blue entry. and that last black entry. Yes, I read it down correctly. I'm really glad you asked that, because I really did not discuss it. I should have.
And then like Brad said, it doesn't really matter if you pull out because in the book it pulls out
It would pull out the 1/3.
magnitude in front of the magnitude of every corresponding.
You know,
Element of
personally, I would not have written the answer the way I've written it. I would have, with my red pen, I would have just rewritten this one entry right here as a 1, 3 plus 3i, and then a 1 minus 1 minus I. It just looks better.
Multiplied by 1/3.
No, leave it as is. I wouldn't have multiplied by 1. I wouldn't have pulled out 1/3. I just leave it as is. Are you denying that this is not a basis? It's orthogonal?
Oh
Yes,
yeah,
okay.
because it's
Look at different magnitudes, and I confess, if the author wanted an orthonormal set, then I'm in trouble. I haven't forced normality with these individual vectors. I'm just simply saying, who cares what the magnitude is? It's not going to change what the relationship is in terms of orthogonality.
Okay.
Do you agree? If you do agree, can we yet again today raise our level of complexity and sophistication? I really do. I want to talk about what it means to consider a vector space. I'll call it V. And how about another vector space? I'll call it W. And I want to look at a transformation, a mapping from one vector space to another. So in other words, everybody, my pretty picture, if I had something like a little v1 in my set uppercase V, and how about a little w1 in my second set w? And if I were to map this one entry to that one entry from the first and second set, I might write notationally speaking that the image of v1 bar under the mapping of T is equal to the corresponding element w sub 1 bar in the second vector space. It looks just like the map B function notation you guys use back in map D. So I don't want to sit here and just restrict my attention to arbitrary mappings. I want to talk about mappings that have very special qualities. I want to talk about a mapping that has a quality that as I transform the sum of two vectors, how about a v1 bar and a v2 bar, that I end up getting the sum of their transformations. So the transformations I want to discuss are going to have this quality. They also have another quality, that if I were to transform, I don't know, how about some scalar times v1 bar, that it gives me in the end the transformation of v1 bar under the mapping of T times the scalar. And if my mapping satisfies those two particular properties, I will subclassify the mapping as a linear transformation. This is a man-made definition. This is not a theorem to prove. A linear transformation. I'll label it T. Mapping from vector space V to vector space W is a linear transformation. Provided both these conditions are met. It's sort of like saying, oh, back in algebra you talk about functions, or excuse me, you talk about relations, but a function is a very special type of relation that has a quality that is single value. Or maybe after you discuss functions, you talk about specialized functions that are maybe one-to-one, even, odd, a couple of different classifications you have for functions. Here, I'm just classifying a subgroup of transformations that are referred to as linear transformations. Yes, Chris?
Why don't we call it a linear function?
I'm really nervous about the word function because when I use the word function, I typically associate that with a mapping sending a set of numbers to a set of numbers. And technically speaking, I'm being really arbitrary here. I have no idea what the vector space V is. Could be polynomials, could be functions. And so I just think it's a better choice of words, so I don't confuse this with functions mapping reals, or excuse me, some number set to some number set. Now I gotta confess, mapping some vector space V into W is a linear transformation. If and only if, when I transpose, how about this linear combination of vectors in big V?
Is the colon actually a symbol for mapping, or is that just?
Oh, good point. It's just I don't know. I mean, it's just a notation I've always used when I describe any kind of transformation mapping one set to another.
Okay.
I suppose you might find some text that maybe use a vertical bar instead. Maybe.
I've seen
I
that
typically
quite
see
a bit,
those.
yeah.
Have you really?
Generally as where, in place of where.
Now, I confess, I do see it typically as well, but only when I typically use set notation.
Yeah.
But I'm not using set notation.
So outside of set notation, it has different meaning.
Yeah, because I don't think those dots really stand for the phrase such now, or the phrase where. It really represents that I've got a transformation mapping the first vector space to the second.
Okay.
And I think I got a linear transformation provided that when I evaluate T on maybe that linear combination of elements of big V, I end up getting this linear combination on elements of big W. To be honest, you guys, I'm just being silly. I think this theorem is absolutely immediate. If you guys don't mind, I don't even want to prove it. I just think it's a direct consequence of having both these linear combinations or linearity properties combined into one. That's all I'm suggesting. And when I use those letters IFF, you guys know what I mean by that, right? If and only if. It means the biconditional statement. Got a linear transformation? Oh, that's got to be true. But if you've got this to be true, it's going to be a linear transformation. It goes both directions. That's all I'm suggesting. You guys, I don't like sitting here wallowing in abstraction, if you don't mind. Can I just immediately dive into some examples? So I want you guys to consider an arbitrary M by N matrix and consider transformation mapping Rn to Rm by just simply having an output where x bar is being multiplied on the left by A. I think x bar necessarily has to be an n-dimensional space because if A is an n by n matrix, then the number of rows of the second matrix has to be the same as the number of columns of the first. That means my x bar has to be an n by 1 matrix, which is just simply a vector of dimension n. So, let's show those linearity properties hold. I think it's a piece of cake. Number one, I think T evaluated on x bar plus y bar is nothing more than A times the sum of those two vectors. But even I in class, when it comes to the summation representation of multiplication of matrices, even I in class proved to you that matrix multiplication commutes over matrix addition. I said commutes. I meant to say cheapers. Matrix multiplication distributes over matrix addition. And so I think immediately I've got nothing more than AX bar plus AY bar. But cheapers, you guys, that's just the transformation of X bar plus the transformation of Y bar. I think to show the other linearity property holds is just as easy. After all, T evaluated to, I don't know, C times X bar is nothing more than A times CX bar. But again, in class, you want to prove that associativity holds. Actually, I misspoke. It's not associativity, is it? That's just a scalar multiple. I get to pull out immediately. And I think I've got nothing more than C times the transform vector X bar.